Dear students, in this session, we are going to see various types of relations. First one is reflexive relation. A relation or on a set is A is called reflexive or is said to be reflexive if A related to A for all A belongs to A. This means for all A related to A. That is A comma A belongs to R if A belongs to A. Consider the relations. These relations R1, R2, R3 are defined on the set A. Here, consider R1 1 1 2 2 3 3. That is A comma A belongs to R. It satisfies this idea. Therefore, we can say R1 is reflexive. Like that, 1 1 2 2 3 3 exists. Therefore, exists in this R2 or the elements of R2. Therefore, R2 is also reflexive. But here 1 comma 1 is there, 2 comma 2 is there. But in on set there is element 3. Here 3 comma 3 does not belongs to R3. So R1, R2 are reflexive. R1, R2 are reflexive. R3 is not reflexive. Since 3 comma 3 does not belongs to R3. Next one, symmetric relation. A relation R on a set A is said to be symmetric relation if A related B implies B related to A for all A comma B belongs to A. That is, A comma B belongs to R implies B comma A belongs to R. For all A comma B belongs to A. That is symmetric. Consider set A, which has three elements 1, 2, 3. Consider relations R1, 1, 2, 2, 1. R2, 1, 2, 2, 1, 1, 3, 3, 1. R3, 2, 3, 1, 3, 3, 1. Here, R1 is symmetric. 1, 2, 2, 1. A, B, B, A belongs to R. 1, 2, 2, 1. 1, 3, 3, 1. So, R1, R2 are symmetric. Here 1, 3 belongs to R as well 3, 1 3 belongs to R3 as well 3, 1 belongs to R3. Here 2, 3 belongs to R3 but 3, 2 does not belongs to R3. Therefore, which implies R3 is not symmetric. Antisymmetric relation. A relation R on a set A is said to be antisymmetric if A related B, B related A, A related B, B related A, which implies A equal to B for all A comma B belongs to A. That is A comma B belongs to R, B comma A belongs to R, which implies A equal to B for all A comma B belongs to A. Next one, transitive relation. A relation R on a set A is said to be transitive relation if A related B and B related to C implies A related to C for all A comma B comma C belongs to A. A is related to B and B is related to C, then A is related to C. That is transitive relation. Equivalence relation. A relation R on a set A is called, or A is said to be an equivalence relation on A where R is reflexive, symmetric, and transitive. Reflexive, symmetric, transitive. Then only we can say the relation R is an equivalence relation. Ordered relation. A relation R is called ordered if R is transitive but not an equivalence relation. Next one, partial order relation. A relation R is called a partial order relation if R is reflexive, transitive, and antisymmetric. At the same time, composition of two relations. If A, B and C are three sets such that are contained in A cross B and relation S contained in B cross C, then S related or S composition or inverse equal to R inverse composition S inverse. Theorems on binary relation. If R is a relation on a set A, then R is reflexive, implies R inverse is reflexive. Like that, R is symmetric, which implies R is symmetric. R is transitive. R inverse is transitive. Next concept, functions. If A and B be two non-empty sets, then a function from A to B associates to each element X in A a unique element f of x in B. And is written as f is a function from A to B, or here function f. One or injective. The mapping f from A to B is called one-on mapping if no two different elements of A have the same image in B. So one-on mapping, or you can say injective. For different elements, we have different images. If x1, x2 belongs to A, then f of x1 equal to f of x2 implies x1 equal to x2. x1 not equal to x2 implies f of x1 not equal to f of x2. Many one. The mapping is called many one mapping. You two are more than two or more than two different elements in A have the same image in R. More than two different elements will have the same image in R, then we can say the function is, or the mapping is many one. If x1, x2 belongs to A, then f of x1 equal to f of x2. The images are equal, but the elements are not equal. On to, that is surjective. So f is a function from A to B. And f of A equal to B that is range equal to codomain. This is domain, this is codomain. If range equal to codomain, then the function is onto and if f of a contained B, that is subset of B, then the function is into. Method to test onto or into mapping. Let f is a function from A to B, be a mapping. Let y be an arbitrary element B and y equal to f of x where x belongs to A. If x belongs to A, f of x belongs to B. Express x in terms of y. Next step, express x in terms of y. Now, if x belongs to A, for all y belongs to B. X belongs to A, for all y belongs to B, then f is onto. And if x does not belongs to A, for all y belongs to B, then f is into. For into mapping, Find an element in B. Find an element of B. Which is not F image. This is the function of F, that means image of F. An element of A. Constant mapping. The mapping F from A to B is known as constant function or constant mapping. Constant function or constant mapping. If range of this function F has only one element. For all x belongs to A, for all x belongs to A, f of x equal to A, where A belongs to B. Identity mapping or function. The mapping F from A to B is known as identity mapping f of A equal to A for A belongs to A. And is denoted by IA. Identity in A. So f of a equal to a or f of b equal to b, whatever take the value, the result will be the same. If you take x, the answer is x. If you take a, the answer is a. Equal mapping. Let f and g be two mappings. F is from A to B and g is also from A to B. If f of x equal to g of x, for all x belongs to A, then the mapping f and g are equal, and written as f equal to g. Equivalent. The mapping f from A to B is known as equivalent if A and B are both one and on 2. And written as A is equal to B. Which is read as A equal B. The function f is both 1 and on 2. We can say also there exists one-to-one correspondence. If f from A to B be 1, 1, on onto mapping, let small b belongs to capital B, then there exists exactly one element A belongs to A such that f of A equal to B. For every element of B belongs to B, there is a unique element in A such that f of A equal to B. F inverse B to A. F inverse of B equal to A if only if f of A equal to B. The function f inverse the inverse of f a function has inverse or a function is invertible, if of, that is if and only if f is one and onto. So the inverse exists provided the function is both 1 and onto. Composite of mapping. Let A, B and C be three non-empty sets. Let if is a function from A to B and G is from B to C. Be two mappings. Then G composite F from is from A to C. This function is called the product or composite of G composite F is called the product or composite of F and G. So F composite of F and G, that is G product F of X for all X belongs to A. Important remarks. F dot G of X means F of G of X, here F of X, here G of G of X. If F G of X means F of X into G of X. F of X plus or minus G of X. F of X by G of X. So G of X not equal to 0. F is a function from A to B. G is a function from B to C. F and G are injective. G dot F is injective. F and G are surjective. Composite of F and G is surjective. F and G are bijective. It's bijective. So we have seen many definitions and results. So So let us start solving problems. For x belongs to r minus 0, 1, let f1 of x equal to 1 by x, f2 of x 1 minus x, f3 of x 1 by 1 minus x, be 3 given functions. If a function f of x satisfies f2 product f1 of x, that is f3 of x, then f of x is equal to option A f2 of x, option B 1 by x f3x, option 3 f3 of x, option D f1 of x. So I have three functions and they have all those three functions satisfies this relation. So you want to find f of x. So f1 of x, that is 1 by x, f2 of x, that is 1 minus x, f3 of x, that is 1 by 1 minus x, f2 product f1 of x equal to is given as f3 of x, which implies f2 f of f1 of x equal to f3 of x, f2 f of f1 of x, we have here 1 by x equal to f3x. So here we know about f of x, f2 of f of x, that is x, f2 of x, that is 1 minus x, which implies 1 minus f of 1 by x equal to f3 of x. You see, consider those whole term as x. We know f2 of x equal to 1 minus x. In place of x, we can write f of 1 by x. One minus f3 of x equal to f of 1 by x. F of 1 by x equal to 1 minus f3 of x. f3 of x equal to 1 by 1 minus x. You take LCM. So minus x by 1 minus, that is f of 1 by x. So minus x by 1 minus, that can be written as x by x minus 1. So f of 1 by x equal to x by x into 1 by x into 1 minus 1 by x. Then this will be x cancelled. 1 by 1 minus 1 by x. So f of 1 by x equal to 1 by 1 minus 1 by x. So we can replace 1 by x by x. Replace 1 by x by x. F of x equal to 1 by 1 minus x. That is equal to f3 of x. So answer option C, f3 of x. So that we have solved only one sum. On 2 sessions we have seen many definitions. The coming sessions we will solve problems. Go through all the definitions we discussed. Thank you.